Hello everyone and welcome to the next lecture. So today's lecture is going to be focused on more advanced indeterminate forms than what we considered the other day. So recall that the previous lecture we considered indeterminate forms of the form 0 over 0 and infinity over infinity, and we developed a really neat rule called L'Hopital's rule that can be applied to evaluating such indeterminate forms. We also showed that this can be extended for limits at infinity. So when we're taking the limit as x goes to positive infinity or negative infinity. And we saw a number of different really good examples of that. So today's lecture is going to be focused on extending this to more complicated indeterminate forms. And I hesitate to say more complicated indeterminate forms because really, they're not that much more difficult to deal with. However, each different type of indeterminate form is going to have its own sort of way of manipulating the expression that we have into the type of indeterminate forms that we discussed in the previous lecture. So this lecture is going to focus on indeterminate forms of the type 0 times infinity. We're going to start with that. And then we're going to consider indeterminate forms of the type 1 to the infinity, and so on and so forth. So we'll also consider indeterminate forms of the type infinity minus infinity later on in the lecture as well. And we'll see how to also cover indeterminate forms of the type infinity to the 0. There are more types of indeterminate forms, but we'll probably just stick with these 4 in the lecture. And the main starting point for us is going to be indeterminate forms of the type 0 times infinity, because the final few is going to, in some sense, depend on 0 times infinity. So we'll be kind of adding to the work that we do at the beginning of this lecture. But let's jump into it and see what we can do for an indeterminate form of the type 0 times infinity. So the idea here is that we're going to be looking at a limit of the form limit as x goes to x naught of some function h of x times some function, we'll call it L of x. This is a product, and if the limit of h of x as x goes to x naught is 0, and if the limit as x goes to x naught of L of x is equal to positive infinity or negative infinity, positive or negative infinity, what we say is that this indeterminate form that we get from this limit, or I should say this limit, yields a 0 times infinity indeterminate form. And the reason this is an indeterminate form, again, like all the other ones that we've talked about, is that really it doesn't have any mathematical definition to it outside of its meaning as this limit. We have to specifically investigate this limit. This limit could potentially be a finite number if h of x goes to 0 faster than L of x diverges to positive infinity. And vice versa, this limit could be positive or negative infinity if L of x grows faster than, or shrinks faster than the h of x function. So I should say if it diverges faster than the h of x function. In other words, if it goes to infinity faster than the h of x function goes to 0. in any case, it's not correct, right, to say that this equals 0 times infinity, because 0 times infinity doesn't have mathematical meaning. The way in which we can deal with this is the following. Right? We can rewrite the limit. We can rewrite this limit here as this limit will always be equal to the limit as x goes to x naught of L of x over 1 over h of x. And what's interesting here is that I've done just a little bit of rewriting. I just rewrote h of x here in the limit as 1 over h of x, which is an algebraically correct maneuver. But now this new indeterminate form is, so this expression right here yields a infinity over infinity indeterminate form. And thus we can directly apply L'Hopital's rule to this quotient right here, which is very, very neat. Because I've just rewritten the limit, but the type of indeterminate form it is changes with this rewriting of the limit. So our upper function here would be our f of x, and our lower function here, 1 over h of x, would be our g of x. You can also rewrite this as h of x divided by 1 over L of x. Which again, right, this yields now a different type of indeterminate form. This is going to yield a 0 over 0 indeterminate form. But what's neat about this trick here is that, and it's really not a trick, it's just an algebraic manipulation. We've successfully turned what's a 0 times infinity indeterminate form into one of our classical infinity over infinity versus, or if we choose the second way of rewriting it, a 0 over 0 indeterminate form. And we can directly apply this L'Hopital's rule that we talked about in the previous lecture to this new expression. So this is the main method here for dealing with 0 times infinity indeterminate forms. Which rewriting we want to choose really depends on the problem that we're kind of considering, the functions under consideration. And we want to choose the rewriting in the way that we get the simplest derivatives when we apply L'Hopital's rule. And that's really just, a matter of practice in terms of understanding which way is going to be simpler. So you really, again, like I mentioned before, want to be familiar and understand all of the basic derivative rules from Calculus 1 when we're going through and doing this. But let's go through and take a look at some basic examples and get some practice. So for the first example that I'll consider, let's look at the limit as t goes to 0 from the right, from the positive. So t is getting smaller and smaller and smaller, of t times the natural log of t. Right off the bat, we can say that this yields a 0 times infinity indeterminate form. And this is because as t goes to 0, well, t as a function is going to 0, so this function is headed to 0, but natural log of t is headed to negative infinity. So the type of indeterminate form that we have here is a 0 infinity indeterminate form. We have two separate ways of rewriting this, like I mentioned earlier. However, the simpler way of rewriting it, I think, and this is just an algebraic simplification right here is the same thing as the limit as t goes to 0 from the positive of the natural log of t divided by 1 over t. This is now a new type of indeterminate form. It's the same limit because all I've done is rewrite t here as 1 over t, but this now yields an infinity over infinity indeterminate form. Because as t goes to 0 from positive values of t, natural log is going to negative infinity, and 1 over t is going to positive infinity. So we have an infinity over infinity indeterminate form. But what's nice about this is we can directly apply L'Hopital's rule, and the derivative of the natural log of t is 1 over t. And the derivative of 1 over t, which is the denominator here, is negative 1 over t squared. So this is our application of L'Hopital's rule. And this now is equal to the limit as t goes to 0 from the positive of t squared over t times negative 1, negative t squared over t, which is the same thing as the limit as t goes to 0 from the positive of negative t, which is just equal to 0. And thus we've obtained the correct value of this limit, and we've shown that this limit in fact does exist, which is very, very neat. Now, I encourage you to go through and verify this in the other direction. Right? If you were to say, have instead of rewritten the limit the way that I did, algebraically rewritten the limit as t over 1 over natural log of t, this would provide you with a perfectly okay way of doing this problem, and you will get the same answer, but the derivatives are just a little bit more complicated, specifically the denominator derivative. The numerator derivative is not too bad, but the denominator derivative is a little bit more complicated in this case. So I think the way that I started with the problem in this way of rewriting is a lot better. But this is perfectly okay to apply L'Hopital's rule to, because this yields a 0 over 0 indeterminate form. But it'd be good practice for you to go through and try this just to verify that you also get 0 if you choose to rewrite it in this manner as well. So what about the next type of an indeterminate form that's a little bit more advanced? We'll start with what to do when you see 1 to the infinity indeterminate form. So this is produced when you have something of the form limit as x goes to x naught of f of x to the g of x, and the limit as x goes to x naught of f of x is 1, and the limit as x goes to x naught of g of x is infinity. Well, in this case, what we do and what we say is that this yields a 1 to the infinity indeterminate form. Right? It's never okay to say it equals 1 to the infinity, because 1 to the infinity doesn't have any mathematical meaning. But what we need to do here is use the definition of what it means to have an exponential like this. And I'm going to use the standard exponential. So let's take a look at what an exponential really means in terms of Now, if you have two real numbers such that a to the b is defined, well, we can rewrite this as e to the natural logarithm of a to the power b, which is the same thing as saying e to the b times the natural logarithm of the base a. And the idea here is that we can directly apply this and actually use it in the limit here. You have this f of x to the g of x is the same thing as the exponential to the power of the natural logarithm of f of x to the g of x. Which is the same thing as the exponential to the g of x times the natural logarithm of f of x. And because of continuity here in the limit, right, we have that the exponential function is a continuous function, and therefore this is the same thing as the exponential of the limit as x goes to x naught of g of x times the natural log of f of x. And so the value of this 1 to the infinity indeterminate form, this limit that we're looking for, is the same thing as the exponential function of the limit of g of x times ln of f of x. And so if we can determine this limit, when we raise it to the power e, we have the exact value of the limit. And what's special here is that the limit as x goes to x naught of g of x times natural log of f of x, this itself is an indeterminate form of the previous type that we talked about. So this indeterminate form yields a 0 times infinity indeterminate form, which we know how to deal with. And it yields in a 0 times infinity indeterminate form because of the fact that g of x as x goes to x naught is going to 0, and g of x is not going to 0, g of x is going to infinity, and ln of f of x is going to 0. That's what's going to 0. F of x itself is going to 1, but remember the natural log of 1 is 0, so this natural log of f of x is going to 0. So this is going to infinity, and this is going to 0. And this yields for us a 0 times infinity indeterminate form. So I'll go over an example of this right now. And this is a really classic example, which is why I included it in the homework for the course. That's a variation on this problem. So we'll consider the limit as t goes to 0 from the positive of 1 plus t to the power 1 over t. This yields a 1 to the infinity indeterminate form because of the fact that 1 over t is going to positive infinity and 1 plus t is going to 1 as t goes to 0. So remember, in this problem, just when we're kind of connecting it to the theory a little bit, the f of x, or the base function here, is the function that's going to 1, and the exponential function, g of x, the exponent, is the one that's going to infinity. So in this example, our f of x is the function 1 plus t, and our g of x is the function 1 over t. And so to get this limit, what we need to look at is the limit of g of x times natural log of f of x. Or the limit of, this should be functions of t, sorry, not x. The limit of 1 over t times natural log of 1 plus t. And 1 over t, as t goes to 0, is infinity. And natural log of 1 plus t, as t goes to 0, is negative, or is 0. So this indeterminate form is, this yields an infinity times 0 indeterminate form. But I would say that this is probably simpler to just rewrite as natural log of 1 plus t over t, which now yields a 0 over 0 indeterminate form. And this now we can directly use L'Hopital's rule on. And when we do this, this is going to become the derivative of 1, natural log of 1 plus t is 1 over 1 plus t. And the derivative of t is just 1. This is after we've applied L'Hopital's rule. And this limit is exactly 1 over 1 plus 0, or 1. Now be careful, we still need to do the final step. Right. Don't forget that this limit that we've just calculated is the limit of g of t times natural log of f of t. The actual limit that we're looking for is e to this limit, the exponential of this limit. So it's e to the power of this limit that we just calculated this limit is just 1, so it's e to the power of 1, or approximately equal to 2.718. And this is incredible because this is actually one of the ways, and there are many ways, but this is one of the ways of exactly mathematically defining what exactly the exponential number e exactly is. Right? Well, what we've just shown here is exactly that this limit is the same thing as the limit of this function is equal to e to the power 1. And in the homework, right, you'll see several different variations on this idea in this type of problem. So what's neat about this is that really this trick can be applied to a lot of other types of indeterminate forms, not just 1 to the infinity. Really, if we have, for some function h of x, this is a note, if the limit as x goes to x naught of ln, the natural log of h of x, is equal to some value, we'll call it the value L here, lowercase l, then we have that we can also write, say, the following. It's the limit of as x goes to x naught of h of x is the same thing as the limit as x goes to x naught of e to the power natural log of h of x, which by continuity is the same thing as e to the limit as x goes to x naught of the natural log of h of x, which is just equal to L. So the limit of h of x is equal to e to the L. Right, and this is for any combination that works, or that gives us a valid limit for the natural log of the function h of x. So what this is saying is that anytime we are looking at a limit of the form f of x to the g of x, even if it's not a 1 to the infinity indeterminate form, as long as the limit of the natural log of this quantity exists, we can get a good valid result here using this method. So I'll show you another example. And this example is going to be of a different type of indeterminate form. We'll look at an infinity to the 0 indeterminate form. So specifically the limit as x goes to infinity of 1 plus 3t to the power 1 over natural log of t squared. This is a little bit more complicated, but basically as x goes to infinity, and I want to use, sorry, not t, but I'll use x. Well, the natural log of x squared, as x goes to infinity, the natural log is also going to infinity. So 1 over the natural log of x squared is going to 0, and then 1 plus 3x, as x goes to infinity, 1 plus 3x is also going to infinity. So this yields an infinity to the 0 indeterminate form. And so to deal with this, immediately what we want to consider is the natural log of the thing we're taking the limit of, and make sure that that limit exists. And if it does, based on the previous note, we'll directly be able to evaluate the limit. So take the natural log of this expression right here. This is the same thing as the exponent, which is 1 over the natural log of x squared. This is the exponent times the natural log of 1 plus 3x. And we can also simplify the natural log of x squared using our logarithm base simplification. So this is going to be the same thing as the natural log of 1 plus 3x over 2 times the natural log of x. And this can, in fact, be directly evaluated in the limit as x goes to infinity. We directly have that the limit as x goes to infinity of this function right here this yields an infinity over infinity indeterminate form, and thus we can apply L'Hopital's rule to obtain the limit as x goes to infinity of this derivative is going to be 1 over 1 plus 3x times 3 from the chain rule. It's the derivative of the numerator and L'Hopital's rule. And this is divided by the derivative of the denominator, which is going to be 2 times 1 over x, or 2 over x. And after a little bit of rewriting here, just a little bit of algebra, we can re-express this limit as the limit as x goes to infinity of 3x over 2 times 1 plus 3x and there are a number of ways of evaluating this limit. You can evaluate this limit using L'Hopital's rule. That's probably the simplest way of doing it. You can also use methods from Calculus 1 in your Calculus 1 class. But sure enough, this limit is going to be exactly 3 over 2 times 3, or 1/2. So remember, this is the limit of this logarithm. It's the limit of the logarithm of what we're looking for the actual limit of. So the actual correct value of the limit, and remember, you need to do this final step right here. This is going to be equal to e to the power of this limit. This is e to the power of 1/2. And this is the correct value of this limit right here as x goes to infinity. So we can see this visualized by going to our Desmos window. You see here I just plugged in the exact function. I also put in one of the asymptotes because this has an asymptote at x equals 1. And we just got a visualization of our point here. And I'll delete the things that we don't need in the proposed limit, which is this e to the 1/2. And sure enough, right, as we get larger and larger and larger for our x values, it sure appears that the x value is approaching this limit. Graphically, we'll kind of, if we go out pretty far, you see it really converge to this limit. And the convergence does take a little while. This is just going up to 100, which is right there. But if I go up to, say, $10,000, for x values, the limit does in fact appear to be getting closer and closer and closer to this actual value. So as we go all the way out here to 10,000, but it does take a while, and this is why graphical methods are normally not the best methods of determining this limit. It takes a very long time for this function to converge down to the limit, as you can see in this plot right here. So really it's fundamental for us to be able to go through and do this using L'Hopital's rule. So the final type of indeterminate form that I'll discuss briefly and just do one example of, just to give you an idea of how to do this, is what's called an infinity minus infinity indeterminate form. And like I've said, there's a number of different other types of indeterminate forms. Really, the possibilities are endless here, but I'm just covering the main ones that you might see in applications when you're dealing with functions and how to deal with them. So for example, if you were to see the limit as x goes to 0 of 1 over sine of x minus 1 over x, this is what's called an infinity minus infinity indeterminate form, where we say it yields an infinity minus infinity indeterminate form because of the fact that 1 over sine of x as x goes to 0 is going to infinity, and 1 over x itself is also going to infinity. So this is headed towards something that's going to infinity minus infinity, which is undefined. So we need to go through and evaluate this using our L'Hopital's rule. And infinity minus infinity indeterminate forms, even though they're the last one that I'm considering, really aren't all too difficult normally, because the main way that we try to deal with these is to rewrite it in some form algebraically, similar to how we've done this previously for the exponential functions. But unlike the logarithmic method for exponential functions, this is really just going to rely on some algebra in bringing this expression to common denominator. So what I mean by that is we want to be familiar with what it means to add fractions. So if you have a over b plus c over d, right, for real numbers, this is the same thing when we bring this summation of fractions to common denominator as AD plus CB over B times D. And this is the fundamental thing that we're going to use here always when adding fractions, and it's why it's very, very important to know and be familiar with. This is really all we're going to do here. So when we rewrite this expression, this is going to be the same thing as x times, x minus, so it'll be this, you get x times x here, x over x, then minus sine of x, all divided by x times sine of x. This is what we get when we bring this expression right here to common denominator. And sure enough, this is a different indeterminate form. This yields a 0 over 0 indeterminate form, unlike the original expression, which yielded an infinity minus infinity indeterminate form. So this is just an algebraic simplification that we've done right here. And so what's nice about this is we can directly apply L'Hopital's rule to it to get 1 minus cosine of x, that's the derivative of the numerator, and then the derivative of the denominator we can get using the product rule. Remember, the product rule says that it's going to be the derivative of x, which is 1 times sine of x plus x times the derivative of sine of x, which is cosine of x. This is applying the product rule in doing L'Hopital's rule for the denominator portion. So the derivative of the numerator is a little bit easier for this example, but you can see how this could directly be applied to a wide number of other examples. And so now we got to reevaluate this and re-look at this to make sure that we're not still getting an indeterminate form. Sure enough, let's take a look at this. So when we plug in 0 here, we get 1 minus cosine of 0, which is 1 minus 1, or 0 for the numerator. And then for the denominator, we're going to get sine of 0 plus 0 times cosine of 0, which is 0 plus 0 times 1, which is also 0. So unfortunately, this appears to be one of those problems in which we have multiple applications of L'Hopital's rule will be required here. We're going to have to apply L'Hopital's rule again. Second application of L'Hopital's rule to this expression right here. Well, the derivative of the numerator is going to be 0 minus, and the derivative of cosine is negative sine. The derivative of the denominator is going to be cosine of x, because the derivative of sine is cosine. And then we have to use the product rule again on this x times cosine of x. So this is going to be derivative of x times cosine of x, which is 1 times cosine of x, plus x times the derivative of cosine of x, which is negative sine of x. It will be minus x times sine of x. So simplifying this up a little bit, we have sine of x over 2 cosine of x minus x sine of x. And you can immediately see that this limit exists because sine of 0 is 0. And when I plug in 0 to the denominator, I get 2 times cosine of 0, which is 1 minus 0. So the limit that we started with is in fact equal to 0. And this is a very important trick because we very often do get this type of indeterminate form in applications, as with all of the other indeterminate forms as well. I'm not going to get into the applications right now, but rest assured you will find limits like this in chemistry, in physics, in engineering, all different kinds of engineering, even in biomedical engineering, in computer science, right? These are very important to understand. One of the big reasons in computer science is what I talked about in the previous lecture, which is orders of growth of algorithms, the speed at which algorithms grow. But rest assured there are many other examples, and I'll give some good examples in class as well. But that'll conclude the lecture for today. Thank you very much for tuning in. I hope you had a great day and learned something.